seminar on applications. So today is my great pleasure to introduce my former PhD advisor, Laurent Bienvenu, who is going to talk about the interplay between randomness and genericity.
All right. Well, thank you, Ludovic, and thank you to the organizers for inviting me. Thank you to all of you for coming to my talk. I do have to confess that somehow it is my first talk that I give on Zoom. I've been using Zoom a lot for personal calls, but this is the first talk I'll be giving using Zoom. I've been doing quite a fair bit of online teaching with Big Blue Button, but I have not used Zoom yet. So please, thank you for your understanding if I do stupid things. I'm going to try my best. Looks like it's working, but we'll see. Okay, so what I want to talk about today is some work that is not like my most recent work, but it was published like more than a year ago in the GSL. This is joint work with Chris Porter, but I haven't had a chance to give a full talk about it. So I thought today was a good opportunity. Okay, so I'm going to discuss the relationship and how two notions interact, the notion of randomness and genericity in computability theory. So maybe I'm having a hard time moving to the next slide. So that's not. Okay, so. So algorithmic randomness and genericity are, as we all know, central concepts in computability theory. Real, what I will call real in this talk is an infinite binary sequence. Is, I say, generic if it is a typical real from the point of view of the category theory, and a real is random if it is typical from the point of view of meta theory. Okay, so that's just like the broad definition, broad idea between randomness, behind randomness and genericity. So more specifically, I will recall the full definitions very quickly because I'm assuming this is a computability seminar, so most of you probably know this very well, but I will just recall it quickly. So more formally, I say that the real is weakly and generic. I put co-en because this is really, effective co-enforcing that we're talking about. So it's weakly and generic if it belongs to every dense 0 to the n-1 effectively open set. And a real is n-generic. So this time it doesn't have, we're not talking about dense open sets. We're talking about all effectively open sets. But X has to belong to either the effectively open set itself or the interior of its complement. And when you take an open set together with the interior of its complement, this is always a dense open set. Not effectively open anymore, but a dense open set. Okay, so it's of course stronger than weak and genericity. This is and genericity. And we have a full hierarchy. So weak 1 generic is implied by 1 generic, which is implied by weak 2 generic, which is implied by 2 generic, etc., etc. It goes up. Same for randomness. So for randomness, for n greater than 2, I say that a real is weakly n random. This time you have to pay attention for uniformly 0 to the n-2 effectively open sets, such that the measure, here mu is Lebesgue measure, right? The uniform measure tends to 0. X does not belong to the intersection of the UN. So in other words, if you want, for example, to take n equal 2, you're weakly 2 random if you're not in every null pi02 set. Okay. And randomness is what you get if you ask that you control the measure of your UN. So we say it is n random. This time, if it's 0 to the n-1 effectively open sets, and the measure of UN is less than 2 to the minus n, and you want that X does not belong to the intersection of the UN. Okay, so these are the basic definitions. And we have a strict hierarchy. Oh, I forgot, no, it's not too generic, it's too random, sorry. It's a copy and paste error. Okay, so random reals and generic reals look very different. Well, basically, a random reel will look random. Like it will look like what you get if you toss a coin, a 0-1 coin. Basically, you will have more or less 50-50 zeros and ones everywhere you look. Even if you convert your reel in another base, in base 3, it will still look like you have 1/3 of zeros, 1/3 of ones, and 1/3 of two, etc. A generic reel will look nothing like this because you're meeting dense open sets. So, for example, a dense open set could be like you have 99% of zeros on some initial segment. This is an open set, so you have to meet that infinitely often, or 99.9%. So basically, if you even just in terms of frequency, of course, there is a lot more properties than that of generic reals, but a generic reel will look absolutely not random, and vice versa. So they're fairly orthogonal concepts in general, and there is a very nice theorem that actually shows that in fact, they're completely orthogonal from level 2 and onwards, that if I take X, a 2 random, and Y, a 2 generic, then they form a minimal pair for Turing reducibility. So in fact, they're like completely orthogonal in terms of Turing reducibility, starting from level 2. Okay, so that could be the end of the story, but of course it isn't. Otherwise, there would be no talk. So this orthogonality is not true for lower levels of randomness and genericity. So generics are always bad at computing random. So that's a given. That's an interesting exercise. A 1 generic cannot compute a 1 random. So of course, a fortiori, a 2 generic or a 3 generic can never compute 1 randoms, or even you can never compute a 1 random. But the opposite is not true. So there are 2 important theorems in that direction. So if you fix a generic Y as generic as you want, there will always be a 1 random X which computes Y. And that's just, in fact, a very special case of the Kuchar-Agache theorem, which says that for any Y, generic or not, you always have a random that computes it. So it's also true for the generics, of course. Okay, so this is the Kuchar-Agache theorem. You can be as generic as you want, you will always be computed by 1 random. And more surprisingly, the first time I heard about this result, that was a while ago, I found it really quite surprising. That now if you take any random X, it always computes a 1 generic, some 1 generic. But it has to be, like X has to be 2 random, at least, we'll discuss exactly how much randomness we need in this talk. But the calculus result is like if you take X to random, any 2 random, it will always compute a 1 generic. Okay, so we see that if we go to lower levels of randomness and genericity, the picture is a lot more complicated than just the perfect picture that we get, minimal pair for 2 random and 2 generic and onwards. Okay, so the question is, okay, then what is this picture? How do they actually interact when randomness and genericity are understood as being between 1 random and 2 random, and between 1 generic and 2 generic? Okay, so this is what we study with Chris. And so basically these are the concepts we'll be looking at. So for randomness, if we want to look between 2 random and 1 random, I'm going to look at 2 important notions, which is Demuth random and weak to random. So weak to random I've already defined. Demuth randomness I will discuss in a second. It's another very important notion of randomness, which has had many applications recently. It's related to strong job traceability. It has motivated some definitions of Oberhofer randomness and balanced randomness, which I will not get into. And actually, if you like the notion that I just talked about, balanced randomness, Oberhofer randomness, they live here between the two. And they're both implied by Demuth randomness and weak to randomness. I will not discuss them in this talk. It's not because I'm lazy. It's because everything I will say in this talk, if you consider the notion that are typically well studied here, Oberhofer random, balanced random, weak Demuth, They will, all the results that all the questions that you may ask about this randomness notion, they will be implied by the results of this talk. So there is a flurry of very interesting randomness notions that live here, but I don't need to discuss them in this talk. Okay, so for genericity, as far as I know, the picture is a little bit simpler, right? Like there's not a big genericity zoo, as far as I know. So there's the hierarchy that I discussed earlier. 2 generic implies weak, 2 generic implies 1 generic. We did find in the literature a notion that I was not aware of, which is PB generic, which was defined by Doni and Jokush. So it's basically weak to generic when you're trying to meet 0' dense sets of strings, except that the bound on the use of 0' is a primitive recursive function. So it's very close to weak to generic. It's just there is a bound on the use. Okay, I'm not going to give the full definition. It's not very important in this talk. I will talk about PB generic, but you don't need to know the full definition. Okay, but I do need to give you the definition. Oh, no, here's my drawings. Oh, I thought they would stay on one slide. Okay. Okay, so to define Demuth randomness, I need to tell you what an omega CA function. So an omega CA function is just a function from natural numbers to natural numbers, which is delta 2. So it has a computable approximation. But I'm asking that for each n, the number when you run this computable approximation, the number of mind changes for g of n is bounded by some h of n for some computable bound h. And so a Demuth test is exactly what you get when you allow the index. So it's a bit like a Martinov test, but you allow the index of your effectively open set to change. So you still have this bound 2 to the minus 10, but you can imagine that, okay, you start building your test, for level n, so a set of measure less than 2 to the minus n, and somebody say, oh, never mind, that's not the open set I had in mind. I'm just gonna start a new one, like forget it. And then you start building another C open set, and at some point you may change your mind. As long as you don't change your mind too often, so bounded by some computable function of n, this is okay. And so that defines a Demuth test. And we say that a real is Demuth random if for every Demuth test. So I want to draw your attention to this. It's not that X does not belong to the intersection. It's like X only belongs to finitely many of these VGNs. So here it makes a difference. When you look at Martinov randomness, it doesn't matter whether you require, like, for passing a test, or to not be in the intersection, or to only be in finitely many of the levels. For Martinov randomness and for several other notions of randomness, it makes no difference. For Demuth randomness, it does. Yeah, if you ask the weaker condition to not be in the intersection, it's what you get is called weak Demuth random. It's much weaker. Okay, so yeah, so this is called the Solovay passing condition. So for Demuth randomness, we want that strong passing condition, which is to only be in finitely many of the VGN. All right, so let's take a closer look at Kautz's result. So I'll recall the theorem. Every 2 random computes a 1 generic. So originally, at least the first proofs I've seen of these results, they use a so-called measure risking strategy, where you kind of like move measure around, and then you color nodes in purple, in blue, in red, and then like you place different amounts of mass, in some sense, of some nodes in your construction, and you need to make sure that you control the amount of lost mass. So it's readable, but it's a bit technical. And the true revelation for me was when Shen, not necessarily in the context of generics, but for other theorems of the same type, explained it to me in terms of what I now call fireworks argument, because Shen used the analogy of fireworks to describe this type of construction. So probably, if some of you have already seen me give talks, there is a non-negligible probability that this talk involves fireworks. And yes, I talk about it quite a lot because I do think it's an important technique. I think it's probably still a bit underused in its applications. I wrote a paper also with Ludovic about this. I also encourage you to read Sasha Shen's original paper. It's a very nice construction. So I will, again, sorry if you know all this very well, but I will probably, just to hammer my point, I'm going to re-explain how fireworks arguments work and how we get Kautzy's theorem using fireworks arguments. So, what's a firework argument? So here's the metaphor. We walk into a fireworks shop, and the fireworks sold are very cheap, but you're suspicious that because they're so cheap, some of them, might be defective. So, what do we want? Well, since they're so cheap, we can ask the owner of the shop to test a few of them before buying one. And what is the goal from our end of the game is either we buy a good one, untested. They say, okay, that's it. I've tested enough. I take this one home. And then when you get home, this time you want your firework to work. Or to expose the owner. They say, haha, see, this fireworks here was defective. And well, then you just sue the owner. That's also a win, right? Now you make even more money. So that's the goal. So how do we win this game? Well, of course, there is no deterministic strategy. If we had a deterministic strategy, let's say like test 2 and buy the third one, the owner could be evil and just always give us, 2 good ones and place a bad one in the third box. So we have no deterministic strategy to win such a game. However, for any delta, we do have a probabilistic strategy which wins with probability at least 1 minus delta. What do? Well, we pick an integer n, which we can even announce to the owner. And I'm going to pick a number k at random between 0 and n. And once I've done that, I'm going to test the first k fireworks. And as soon as I get a bad one, if I do, I say, okay, that's it, game over, you've lost. Now I will sue you for trying to sell me bad fireworks. Right? If they're all good, then you buy the k plus 1. Okay? So why is this good? Well, this is a good strategy because what is the only bad case scenario for us? Right? The only bad case scenario is when we just happen to buy the k plus 1, and k plus 1 was exactly the position of the first bad box. Because if the first bad box came before the k plus 1, then we would have won by finding the bad one earlier. And if the k plus 1 is a good one, then this is one we take home. So we also win. So we would be only unlucky if we somehow happen to have chosen k in a way that k plus 1 is the position of the first bad box. Okay, so that's the reason why the failure probability of a strategy is just 1 over n plus 1. Right? It's just like we just somehow picked the bad k between 0 and n. Okay, and in fact, you can show that's an interesting scenario. Like if there are exactly n fireworks to be bought in the shop, this is the optimal strategy. This is like the von Neumann equilibrium. Like the owner should pick one bad one at random between 0 and n, between 0 and n, 0 meaning that it doesn't have a bad one. And our strategy should be to do exactly this. So it's in fact an optimal strategy. It's not important here, but it's an interesting result that it's in fact the best strategy we can have for the fireworks game. Okay, now of course the question is, what does this have to do with genericity? Because this is completely not obvious. So we want to construct a one generic using a probabilistic strategy. Right? This is what we're going to do. We're going to say that we have a strategy which is probabilistic but otherwise computable. It's just we use some randomness, and we want to build a one generic. So we look at we take an enumeration of all seed sets of strings, and we want to satisfy that we're going to build construction of x. So either for some n we have that x to the n is in SE, or for some n, no extension of x to the n is in SE. right? That's our requirement for the E set of string. So we were going to build, sorry, I mixed up. I wanted to change the name to Y, but now it's all mixed up. So we build our sets by finite extension. So initially we start with the empty string. And what are we going to do? So we fix our failure probability delta, right? We were going to devise a strategy to do this for any delta. So we fix delta positive. And I'm going to choose a bound QE delta for each requirement E in a way that the sum of 1 over Q of E delta is less than delta. And I set an error counter to 0 for requirement RE. Now, what is my step 2? Okay, so when I start addressing requirement RE, I suppose I've already built some initial segment, sigma of X. And I'm going to make a passive guess. I'm going to say, okay, I feel confident that my sigma is good in that there is no extension of sigma in SP. So if that is the case, I win. Right? My requirement is satisfied. My X will be in the interior of the complement. So I'll be good. So this step here, this step A, is the equivalent of testing fireworks. I say, okay, for the case time, I'm going to test the hypothesis that there is no extension of sigma in SP, right? And then I start handling all the requirements. This is I'm just waiting to be proven wrong. If I'm never proven wrong, then I win. So this is the equivalent of being proven, like having said this is a bad fireworks and being correct about this, right? So this is the step A is the passive guess. It's like, okay, I say that I win the requirement just by SE to be defective in some sense, that it will produce no extension of my sigma. Okay, and I start doing other things. And at some point, so that's the analog of the fireworks going off. It's like, oh, I was wrong. There was actually an extension of sigma I could have picked, but this is too late because I started handling other requirements. I've done other things. Maybe now I've moved past sigma. I was continuing my construction, and it's just too late for me to take the extension in SE. So what do? I say, well, I'm going to make another passive guess, just testing more and more fireworks, right? And I continue like this. And every time I'm proven wrong that there was an extension in SE, I increase my error counter by 1. And at some point, I reach the threshold that I had agreed, that I had chosen in advance at random. Is my KE, right? I say, okay, I've been proven wrong too many times. Now is the moment of truth. Now I say, fine. Clearly, there always seems to be an extension of sigma in SE every time I make the passive guess. So that's it. I've had enough. I stop everything I'm doing. I focus on this one requirement. And I'm just going to wait for some extension of my current sigma to appear in SE. So yeah, this is the moment. And we wait. Stop everything else we're doing. Say, it seems that SE keeps being dense above me. So I'm just going to go for it now. Right? And we wait for an extension to appear. If it does, then I take it. This is the analog of taking fireworks home. I say, okay, I take that one. And there is, of course, it's a risky strategy at this point. It's a risky move because what could happen is that we could be proven wrong and say, in fact, there was no extension tau that will appear in SE just when we go for it. And that's the losing case in the fireworks strategy. Okay, but this, just like in the fireworks simple game, there's only one bad choice, right? There's the one bad choice that you can make for your threshold KE is exactly the number of times you can be, like the first time you stop is exactly the first time there was no extension in it, right? There's just one bad value every time. Okay, so that's what shows why the algorithm works, is because the losing case is to get stuck at step 3 And the probability for this requirement is, well, 1 over the bound that we've chosen, Q of E delta. And we chose Q of E delta in a way that the sum of probabilities is less than delta. So this probability of global probability of failure is bounded by delta. Okay, because every other case makes me satisfy my requirement RE. Either I correctly guess that there was no extension to be taken, or I correctly guess that there was an extension to take and I take. Okay, so from an algorithmic perspective, this shows that with probability as close as I want to 1, I produce a 1 generic. So let's say if X is sufficiently random and I use X as a random source, I will produce a 1 generic. Now, of course, the question is exactly how random does X need to be, right? So suppose I'm building my Y using the bits. So here, X really is the random generator, right? I use X as a random generator, and I build a Y as in the fireworks construction, and I use X to help me with my choices. When I say, oh, I'm going to pick something between 0 and the bound, I'm using X to do that, right? Just some random bits. So that's exactly what you do with a computer when you need to make random choices. You just generate random bits and then you use them, right? So what does the failure set of the algorithm look like? So if you focus on one requirement RE, what is the set of X's that make the algorithm fail because of this requirement? Remember, when we lose, it's because we get stuck in the steps 3 of some RE. Well, the set of X's that make you get stuck in RE. So we know it has small measure. That's the probabilistic analysis. But from a computability perspective, what is the failure set? It's a difference of 2 open sets. So it's a difference of UE delta, the set of X's that make you enter step 3 of the algorithm. So after reading finitely many bits of X, you say, okay, now we're going to enter the step 3, where we just go for it. But there is a way out of this step 3, is to win by finding an extension. And that's the set of X's that make us enter step 3 and succeed. Right? There is some X's that will make us enter step 3, but then we'll get stuck. But some X's will make us enter step 3, and they're good, because we can also win at step 3 by finding the correct extension. Okay, so the failure set is a difference of 2 sets. It's the thing that make us enter minus the thing that make us enter and succeed there. Okay, so how do we put things together? Well, now I can just look at all the combination of En, and I can look at the failure set of the algorithm for requirement RE, right, for error bound 2 to the minus n, right, because I have one algorithm per bound, right? So now I look at the set of things such that the algorithm with measure bound 2 to the minus n gets stuck in RE, and I look at all the possible pairs, right? So I pick the function q in such a way that the measure of fk has measure at most to minus k, and then I put all of them together. I consider the test of all the fk. So fk is the differences of open sets. And I say my x passes the test if it only belongs to finitely many fk's. If it does, then that means that for some n, x is not in any of the failure sets f of the n. That is, the probabilistic algorithm with error bound 2 minus n succeeds when using x as a random source to produce a 1 generic. So if x passes the test, then x computes a 1 generic. Okay, so that means we have a randomness notion which guarantees being able to compute a 1 generic. It's to pass this type of test. So when we analyze the fireworks argument, we say, okay, well, we know that type of test. These are called the difference tests that were introduced by Franklin and Ong, where every level of the test, you want measure 2 to the minus k at most, and it's a difference, it's one CE open set minus another CE open set. However, in difference randomness, the classical notion of difference randomness, you don't use the passing condition to be on infinitely many, but you use the weak passing condition, which is to not be in the intersection. So for difference randomness, we look at the same type of test, but we ask that X does not belong to the intersection of all the FKs. And very interesting notion of randomness. It's equivalent to being not enough random, being one random and not compute zero prime. But here we have a stronger passing condition. So we decided, okay, we're going to define strong difference randomness. So it's difference randomness with a strong passing condition that I want for every difference test. I belong to only finitely. Okay, so this is where we advertised that definition a little bit, but what we had missed, and I would like to thank Mathieu, who is in the audience, for pointing this out a couple of years ago, that this is not a robust notion. So unlike Demuth randomness, 2 to the minus n is not, the notion of randomness we get is not independent of the bound to the minus n we put, right? Demuth randomness is, so we use 2 to the minus n, not enough randomness is, difference randomness is, so there, for most definitions of randomness, like we use 2 to the minus n because, well, why not? But in this case, it does matter. So we, for Demuth randomness, yeah, for example, you can replace minus n by 1 over n squared. All you need is to be able to apply the Borel-Cantan dilemma, and you want the sum of the probabilities to be finite. Okay, but here it doesn't matter. Why? Because typically when we want to prove the equivalence between two bounds, then you need to kind of group several levels together, right? But here our levels are just a single union, a single difference, one open set minus another open set. So if I start grouping them, well, it's no longer a difference of two open sets, it's just a finite union. So that's exactly the two options I have. So the first option, you say, okay, clearly the bound to the minus n it's not an arbitrary choice, so I should quantify over all possible bounds. So this time I should define a strong difference test to be a sequence of differences of effectively open sets, such that the measure is, not that the measure is uniformly computable, but we have a uniform bound over K, and the sum is a computable real. Yeah, no, forget about this one. I meant like bounded by some computable bound, right? And most importantly, that this is a computable real, right? So I should allow not only 2 to the minus n, but 1 over n squared, 1 over n cubed. All of these should be allowed to be strong difference tests. And then to define strong difference randomness as being this. Or the option 2, if I want to keep the bound to minus n and I want to say, okay, well, this is a robust notion, then I should allow the trick that we use for Demuth test, which is to group several levels together. So that I should allow my FKs not to be finite unions of differences of effective open set, not just differences, but finite unions of differences of effectively open sets. So that's my second option. So the first option is probably what we should call from now on strong difference randomness. And well, it remains to be studied. I am not really aware of any work that uses this definition. There's been some very interesting recent work by Ethan McCarthy, but he used, I believe, the old definition with 2 minus n. I mean, it is a definition of randomness, just not very convincing why it seems a bit arbitrary, right? Of course, you can always define randomness that way, but why 2 minus n and why not 1 over n squared, right? So to really be talking about strong difference randomness, you would need to quantify over all possible acceptable types of that. Right, but we also have the second option, and we started looking at the second option, and then we were able to prove that, in fact, the second option, when you look at tests of this shape, it's just Demuth randomness. Takes still a little bit of work to figure it out, but essentially, this is just a Demuth test. So, well, there you have it. That answers, that was originally a question of Montpellier yesterday and Louis Pye, that every Demuth random passes the test of the type that I just mentioned. And therefore, they are enough as a random source to make the fireworks argument go through to construct a one generic. So every Demuth random real computes a one generic. So we have improved a little bit Kautzy's result. You don't need two randomness. All you need is Demuth randomness. Okay? And what we get is a one generic. So the question is, okay, if we keep Demuth random, but we want to increase a little bit, the genericity notion, can we do better? Then the answer is no. One generic, really, for the known hierarchy of genericity, this is the best you can do. If you take Demuth random and you just go a little bit higher for genericity, just say PB generic, then immediately you have a minimal pair. So it's still a very nice thing that we can compute one generic, but we should not fool ourselves. We cannot really go much higher. So don't have time to do details on that, but the result is kind of tight for Demuth randomness. Now, okay, remember in my diagram, I had two things of interest between one random and two random. I had Demuth randomness and weak to randomness. So Demuth randomness, we understand now fairly well. They all compute a one generic, and they all form a minimal pair with PB generic. Now, how about weak to randomness? And for weak to randomness, the interesting thing is it's complicated. They don't all agree on that. Not all weak to random agree, right? For the Demuth randomness, they were all in agreement. They all computed one generic, and they all form a minimal pair with PB generic. So in a way, they behave kind of uniformly in the blob of Demuth randoms. They behave uniformly, towards genericity. Right? For weak to randoms, it's completely different. There are weak to randoms that will see compute very generic reals, and there are weak to randoms that absolutely do not. So one end of the spectrum is you have weak to randoms that are of hypermuon free degree. So that's folklore. But what does that in particular imply? It implies that they won't even compute a weak one generic. So very, very bad at computing generic. So some weak to randoms are really bad. Like they're hypermuon free, they compute no weak one generic. Okay? But at the other end of the spectrum, we have some weak to random that compute even a two generic. So that's the argument for that is interesting. So it has two parts. This is not my work, so I want to take the time to explain how it goes. So the first part is to understand that for the levels of randomness of genericity between one generic and two generic, there is a very interesting correspondence between the ability to compute them and the ability to compute functions that are difficult to bound. So in some sense, like at these levels, genericity and some sort of hyperimmunity are equivalent, right? So the formal definition is I take a family of functions from n to n, and we say that x has f escaping degree if x can compute a function which is not bounded by any member of this family. So for example, delta 01 escaping, if you take all the computable functions, escaping, not being bounded by any delta 01 function is just having hyperimmune degree. Okay, but you can do that for other families. And in fact, then you get a very nice correspondence. So courts back in the days proved that the ability of computing a weak one generic is just the same as have a hyperimmune degree, so delta 01 escaping. But Doni and Jokush say, oh, but PB generic is the same. It's the ability to escape omega CA functions. So I define omega CA, so that gives a complete characterization of PB genericity in terms of some sort of hyperimmunity. And Andrews, Gerdes, and Miller push that further to weak to generic. So weak to generic is delta 02 escaping degree. And the last one is not an if and only if, but it's still if you're sufficiently hyperimmune that you can compute a two generic. So if you escape delta 03 functions, then you compute a two generic. Okay, so for levels up to two genericity, the ability to compute a generic is equivalent to escaping a family of functions. So that's part one of the argument. And part two is, well, probably what was a surprising theorem at the time of Bombardier, Doni, and Hong, that for any countable family of functions, you have a weak to random which can escape this family. So, well, if you put, so we saw that there was, on one side, we have the hyperimmune free weak to randoms, and on the other end of the spectrum, you have these weak to randoms that just compute wild functions that are super hard to bound by any level, any computability level. So if I put the two parts together, then I have the existence of a weak to random which computes a two generic. Okay, so weak two randoms, they go from not even being able to compute a weak one generic to some of them being able to compute a two generic. So that's very surprising. And can we do more than two generic? Well, the answer is maybe, but not directly using the result that I mentioned by Bompalius, Donnet, and Ong, because, and that's a very, fairly recent theorem, and I find it really fascinating, is like the correspondence between hyperimmunity type things and computing a one generic stops after two generic, very abruptly, I should say. So if we saw that up to two generic, there is a correspondence between escaping some family of functions and computing a generic. But at weak three generic, this is over. There is no countable family of function, which such that if you can escape it, then you compute a weak three generic. So you cannot just use the Bompalius, Donnet, and Ong theorem to prove that, say, there is a weak two random which computes a weak three generic, because escaping function is not good enough. But nonetheless, we were able to revisit the Bompalius, Donnet, and Ong theorem and prove that, in fact, it's for weak two randoms, we can do better than just escaping a set of functions. We can just compute any element of a Comigor set. So for every Comigor set G, we have a weak two random which computes a member of G. So for example, you can take G to be, N42 generics, or delta 1,1 generics, or something really, really generic. And you will always have a weak two random which will be able to compute a member of this family. All right. Well, I originally wanted to give some hints about how this construction went, but it's fairly technical, and I have used already 45 minutes, so it's probably better that I stop here. So I will just put the final picture. So now between one random and two random, and between one generic and two generic, we have a fairly complete picture at this point. And like I said, if you're interested in other notions like Oberhofer randomness or weak Demuth randomness, then you will find the answer you're looking for as a corollary of this, right? So for n random, and n random forms a minimum for more than two, it forms a minimal pair up to PD generic, but then one generic is always computed by two random. Same is true for Demuth random. From that point of view, Demuth random and two random behave quite similarly. Weak two randoms, on the other hand, they may compute or just may not. So for all of them, and the same is true for one random. And I should add, as a teaser for this talk, that there is still this central open question which is open, which would strengthen our result that every Demuth random computes a one generic. What we do not know is it just because a Demuth random is always of hyperimmune degree, or is there another reason? Is it enough to have randomness and hyperimmunity together to compute a one generic? Right? We know that a Demuth random must be hyperimmune. That's fairly easy, right? But so is this just what we need? Is it just because Demuth randomness gives us hyperimmunity, or is there more to it than that? So as far as I know, this is still an open question. I mean, I remember discussing it very recently with Jon Greenberg. I believe it's still open. So that would be a stronger result that every Demuth random computes one generic. And it's not really clear how to use this in some fireworks argument, because at the end of the day, a firework argument would be for almost all X. And well, I guess you could imagine building a type of test that would have, that you would pass if you're one random and hyperimmune, but it seems a bit difficult. So anyways, I just want to put this question back on the table, and thank you for your attention.
Okay, thank you very much for this talk. It's very nice to see that there is such a clear picture on the interplay between randomness and genericity. So does anyone have questions?
Well, this is not really a question, but first I want to thank you for a very fine talk, Laurent. But this fireworks strategy reminds me of something else, and maybe there's not that close a connection, but it's the secretary's problem, which you may have heard of.
Sure.
You need to hire a secretary, and you know the number of applicants, N, but you don't know anything about them until you interview them. And once you interview a candidate, you must either hire that candidate or completely forget about them. They will go elsewhere. And if I recall, the best strategy is to interview the first N over E candidates and choose the first one, which is better than all the previous ones, or something like that.
It's exactly that. That's So that's indeed the secretary, so-called secretary problem, when you want to hire a secretary for people, and so you imagine that you have a total order over them, but you don't know that order in advance. So you can only tell if when a new secretary comes and a new candidate is interviewed, whether how it ranks compared to the one you've already seen.
Right.
And your goal is to hire the best one.
Right.
And no matter what is amazing is no matter how large your pool of candidates, you have a 1/E probability to hire the best one by sampling the first 1/E candidates and then take the next one that beats all of them after.
The first N over E.
The first 1/E fraction of. Of course, 1/E is not even an integer. So you first sample the first, what is that, 37% candidates. You just commit to not hiring any, but then you take the first one after this first 30, I think it's 37%, which is better than your sampling pool. That could play a role. I mean, it would have to be in a construction where we are trying to maximize something. That's typically not what we do in computability theory. I guess we're always trying to meet something, and if we meet, we're happy. But if we were in a situation where we try to build the best something, could be interesting. Like maybe some kind of infinite version of the secretary problem, or maybe with a weird order. I don't know. Maybe something to think about. It's the same type of thing. It's a probabilistic algorithm. Of course, another general question that I have is, well, the fireworks argument really is, as far as I know, the only convoluted application of a probabilistic algorithm to computability theory. And whether it's a secretary problem or the types of probabilistic algorithm, can we find another different family of probabilistic algorithms that come up in
there is
theory of algorithm that could have application. So it could be the secretary problem, it could be something else. Yeah.
The Runyan-Shevchen effectivization of the Lovász local lemma, which various people and I use to look at the showing that a certain version of Heinemann's theorem, where you limit the length of the sums, is not effective. It's not computably true.
So absolutely, except that the problem here is that it's not really that you use it's not the probabilistic algorithm which is key. It's the de-randomization. So in some sense, it's effective. So you have this probabilistic type of argument that you can make in a way that it becomes computable, actually, right? And so that's kind of like going the other way around in some sense. The Runyan-Shevchen argument is like, if you have this type of probabilistic process, then in fact you have a computable solution. So yeah. I mean, it's, I guess in a way, it is a little bit using probabilistic algorithm, but at the end of the day, you don't really need any randomness at all. It's like the randomness is just used as a justification for why you can compute something. So it's probably of slightly different nature. Because I guess if you go down that path, it's just like the original Sachs result, that if you can compute something with positive probability, then you can just compute it at all without. So that's more like a de-randomization theorem, I would say, the effectivization of the Runyan-Shevchen. So here, what I'm asking is, can we have other algorithm where it is key to be seeded by a really random real and to get something interesting, like an interesting object in computability. So.
Okay, is there any other question?
I have just another comment that seems to fit. First of all, really nice talk, thank you. And my comment is that if a real is one random, but not weakly two random, then we also know that it computes a one generic because result of Hirschfeld and Miller is that it computes a non-computable CE degree.
Yes, that is true. Yeah, being weak to random is the same as being one random and not compute any non-computable C set. So yes, if you compute a non-computable C set, then you also compute a one generic. So you are correct. So yes, so that's another way to approach the open question that I mentioned. Yes, thank you.
Okay, so if there are no more questions, so thanks again for this talk.
Thank you.
So as usual,